1988. Duncan Haldane draws a honeycomb on a sheet of paper. The lattice carbon makes, hexagons sharing their edges, and then does something that ought to be against the rules. He threads a magnetic field through it, pointing up through the middle of each hexagon and down again around the rim, arranged so that the total flux through one cell of the lattice comes to exactly 0. Hold a magnetometer over that sample and it reads nothing. Carry an electron once around the boundary of a cell and it comes home with no extra phase to show for the trip. And the Hall conductance of the filled band comes out at 1 times the electron charge squared over Planck's constant, a quantum Hall effect with the magnet taken away.
The title is almost a taunt, model for a quantum Hall effect without Landau levels, and the subtitle offers it as a condensed matter realization of the parity anomaly, then a piece of particle physics. Haldane saw that the room-sized magnet was doing 2 jobs, and everybody ran them together. One was chopping the motion into Landau rungs. The other was breaking time reversal symmetry, making an electron's clockwise circle different from its anti-clockwise one. Only the second is load-bearing, the first is scaffolding. Take a crystal that already has bands, break time reversal inside it by other means, and the Berry curvature over the zone is no longer forced to cancel, and the sum of it need not be 0.
There is something about the flux I do not want to slide past, because 0 through a cell is not 0 everywhere. If an electron going round the whole hexagon picks up nothing, and yet the field is genuinely up in the middle and down at the rim, then a smaller loop drawn inside that cell must enclose something.
It must, and that is where the entire effect lives. The phase around a small loop is not 0, only the sum around the unit cell is. In the arithmetic, it is a hopping amplitude between next nearest neighbors carrying a complex phase. An electron picks up one sign going one way round a triangle and the opposite coming back. That asymmetry between the 2 senses of circulation is what breaking time reversal means, and it is the only ingredient the model has. No net field, no Landau rungs, no magnet in the building.
How long did it take anybody to build one?
Haldane presented it as unlikely ever to be realized, an existence proof that the integer needs no uniform field. 25 years later, 2 experiments arrived. In 2013, Chang Sui Zhu and colleagues in Xue Qi Kun's group at Tsinghua took a thin film of bismuth antimony telluride, doped it with chromium so it became magnetic of its own accord, cooled it to a few hundredths of a Kelvin, and watched the Hall resistance sit at Planck's constant over the charge squared with nothing applied. The following year, a Zurich group built the honeycomb itself out of cold atoms in a laser lattice, shaken in a small circle to supply the broken symmetry, and read off the sideways drift. Haldane shared the Nobel Prize in 2016.
That is the anomalous version, and it is a genuine achievement, and it has not moved the problem I actually care about. The magnet has been made smaller and put inside the crystal instead of around it. Time reversal is still broken. Every argument from the Hall bar carries straight over because nothing structural has changed.
Nothing structural has changed, which is why the next question is worth an hour. Do not break the symmetry. Keep time reversal exactly intact. No magnetism, no field, nothing in the room to switch off, and ask what is left.
What is left is nothing, as far as I can see. Time reversal forces the Berry curvature at one momentum to be minus the curvature at the opposite momentum. Add that over a zone which maps onto itself when you flip the sign of momentum, and every contribution has a partner cancelling it exactly. The integral vanishes. The Chern number is 0 in every such material, always. Why is that not the end of the conversation?
0, and not approximately 0, exactly, by symmetry, in every time reversal invariant band insulator, that has ever existed or ever will. So the Chern number cannot be what distinguishes them. What that real theorem does not show is that all such insulators are the same insulator. It shows that one label is blind.
Which is a much weaker statement than the one I just made, and I made the stronger one without earning it. Is there a precedent for a quantity vanishing and something surviving underneath it?
A familiar one. A molecule with no electric dipole moment can still have a quadrupole, and the quadrupole is not a small correction to a dipole. It is a different object, obeying different rules, and the vanishing of the first is why you go hunting for the second. Here it is sharper, because what survives is not a smaller version of the same quantity. It is a number with two values. Not how much, whether.
Two values. So whatever is being counted, it is only being counted up to whether it comes out even or odd. What could conceivably be even or odd about a band structure?
The way in is to build the state rather than classify it, because the construction is the thing you can picture. Charles Kane and Eugene Mele at Pennsylvania, 2005. Two papers, 7 months apart in the writing. The first is about graphene and hands you the picture. The second is where the invariant gets its name.
Graphene is the honeycomb. So they are taking Haldane's lattice and doing something to it that does not involve a magnetic field.
Doing something to it that a carbon atom does by itself, which is the beautiful part. An electron moving through a crystal sees the electric fields of the nuclei. In the electron's own frame, those static fields look partly magnetic. A charge you are moving past is a current, and a current makes a field. So a moving electron feels an effective magnetic field of its own making, and it couples to its spin. Spin-orbit coupling. It is in every atom, entirely internal, and there is nothing to switch on.
If it acts like a magnetic field, I would expect it to break time reversal like one, and then we are back where we started with a smaller magnet.
It does not, and the reason is the hinge the whole hour swings on. Runtime backwards. The electron's velocity reverses, so the effective field it makes reverses too. And its spin reverses because spin is an angular momentum, and angular momenta flip when you reverse time. Two minus signs. The coupling between them is unchanged. An external magnet does not care which way the electron is going. This is a field manufactured by the going. That is why it can act like a magnetic field on each electron separately, and still leave the whole system symmetric under reversing time.
So a spin-up electron and a spin-down electron see fields pointing in opposite directions.
Which is the entire Kane-Mele construction in one sentence. Take Haldane's model and give the electron a spin. The spin-up electrons see one sign of the effective flux and land in a Haldane model with Chern number +1. The spin-down electrons see the opposite sign and land in one with Chern number -1. Two copies, mirror images, stacked in the same crystal.
And the total is 0, as the theorem insisted. But the edges are not 0, because each copy separately has to obey bulk boundary correspondence. The spin-up copy has an integer inside and 0 outside, so it must run a one-way channel around the rim. The spin-down copy must run one too, and its integer has the opposite sign, so its channel runs the opposite way round.
So on any edge, there are two channels rather than one. A right mover carrying spin up and a left mover carrying spin down, sitting on top of each other in the same few nanometers of boundary. The net charge current at equilibrium is nothing. The net spin current is not, which is where the name quantum spin Hall came from. And the invariant is the Chern number of the spin-up sector alone, which is +1. And that is what distinguishes this insulator from an ordinary one.
Held together by spin being a good label. In a crystal where the electron's spin is coupled to its motion, why would the component of spin along any fixed axis be conserved at all?
It would not be, and the answer I just gave you is not the answer. What I described requires the spin along one axis to be a constant of the motion, and in any real crystal it is not. The term Kane and Meillet wrote for graphene happens to conserve it, and the moment you add anything realistic, a Rashba term from the substrate, a bit of buckling, the sectors mix and the spin-up Chern number stops being defined. That number is a scaffold, not a result. Their second paper exists because the first one's construction does not survive contact with a real material.
And when the sectors mix, the two channels on the edge are no longer independent. A right-moving electron can find a bit of left-moving amplitude in itself, so there is nothing left forbidding it to turn round, and the edge should gap out and become an ordinary insulator like everything else.
That is the expectation. It is what happens in most of physics, and here it fails. The two channels cannot gap each other out, and the reason is a theorem from 1930 with nothing to do with topology. Hendrik Kramer's. In any time reversal symmetric system made of particles with half-integer spin, every energy level is at least doubly degenerate, and the two partners are exchanged by reversing time. Not degenerate by accident, not to within a small splitting. Exactly degenerate, forced.
The right mover and the left mover are that pair. One is what you get from the other by running time backwards, since reversing time flips both the direction of travel and the spin.
A Kramer's pair and a gap between them is a splitting between them, and a splitting is exactly what Kramer's forbids so long as time reversal holds. You may push the two channels around, bend them, move where they sit in energy. You may not separate them. Something that would ordinarily be destroyed by the first perturbation you write down turns out to be nailed in place by a symmetry nobody put there on purpose.
A protected edge with no magnet and no field. If that survives everything I can throw at it, I want to know what the invariant even is, because the spin Chern number has just been withdrawn, and I am holding an edge with no bulk quantity attached to it.
Before the invariant, one more case, because it decides the shape of the answer. Suppose the edge carries two Kramer's pairs instead of one. 4 channels, 2 right movers and 2 left movers. Right movers spin up and left movers spin down as before. Does that edge conduct?
Twice as well and twice as safely. Each pair is a Kramer's pair. Each pair is separately pinned by the same theorem, and the theorem does not know or care how many other pairs are standing next to it. So both survive. The conductance is 4 times the charge squared over Planck's constant, and if anything, the state is sturdier than the one-pair version, because there is more of it.
The conductance is 0. The edge is an ordinary insulator, and an impurity with no magnetism in it whatsoever will do the job. Kramer's protects a state against being split from its own partner. The right mover of the first pair is not the partner of the left mover of the second. Its partner is the left mover of its own pair. So the matrix element turning a right mover of pair 1 into a left mover of pair 2 is forbidden by nothing. It scatters, the two pairs hybridize, a gap opens across all 4 channels, and the edge stops conducting.
I gave the theorem a job it was never doing. It protects a couple against being separated. It says nothing at all about a couple being introduced to another couple, and the 4 of them rearranging themselves into 2 boring pairs with a gap in between.
2 pairs annihilate. 4 pairs annihilate 2 at a time. 3 pairs annihilate down to 1 and stop, because the last one has nobody to pair with. And 1 is 1 forever.
There is the even and the odd. The invariant is not how many channels the edge has, because that number can be changed by chemistry, by disorder, by pressing on the crystal. It is whether that number is odd, because the moves available only ever remove them 2 at a time.
Which is a genuine invariant with 2 values, and the central object of the hour. The mathematician's name for a quantity valued in even and odd is the integers modulo 2, written Z2, so the label became the Z2 invariant. An ordinary insulator is even, 0 pairs, or 2, or 4, all of which can be swept off the edge without closing the bulk gap. A topological insulator is odd. Kane and Melle's second paper, autumn of 2005, says it in the title. Z2 topological order and the quantum spin Hall effect.
The edge version I can hold. What I do not have is the bulk version, and I need it because the whole force of the Chern number was that you computed it from the filled states deep inside a sample, and it then told you what the boundary had to do. An invariant I can only get by looking at the boundary has lost the thing that made it worth having.
It exists, and it is genuinely harder to picture than the Chern number, which was an integral of a curvature over a surface, a geometrical quantity with an area under it. This one is not an integral of anything. It is a statement about how the wave functions at momentum k and at minus k are stitched to each other across the zone, and whether that stitching can be undone smoothly or has a twist in it no smooth change removes.
A twist with no curvature under it. Is there anything I can hold that behaves like that?
Take a strip of paper, glue the ends, and you have made a cylinder or a Mobius band. Both are strips of paper. Both are perfectly smooth. The number of half-turns is not written at any point on the surface. Every small patch looks identical in the two cases, and yet no amount of gentle handling turns one into the other, and the only thing distinguishing them is a count of twists modulo 2. Time reversal supplies the gluing rule here, pairing each momentum with its opposite, and the invariant asks whether the band structure has been glued up with a twist.
Is that computable, or is it the kind of definition that is admired rather than used?
For 2 years it was closer to the first than anybody liked. The original definition counts the zeros of a function over half the zone, and it is correct, and it is horrible. Then Liang Fu and Kane, 2007, found the shortcut that changed the field's working life. If the crystal has inversion symmetry, flipping every coordinate through a lattice site leaves it unchanged, which many real crystals do, then all you need are the momenta that map to themselves under that flip, 4 in 2 dimensions and 8 in 3. At each, every filled state is either even or odd under inversion, and the 2 members of a Kramer's pair always agree. So take one from each pair, multiply those signs across all of them, and the answer is plus or minus 1, and that sign is the invariant.
Signs read off at 8 points in the zone. That is not an approximation to the twist, it is the whole of it.
The whole of it, when inversion holds, which is why the search for these materials stopped being a matter of intuition. You run the standard band structure calculation, look up the parity of the occupied states at 8 momenta, multiply, and the computer tells you whether the crystal you have never grown will have a conducting surface. Materials were predicted before they were made, which is not the usual order of business here.
What is doing the work in that formula? Multiplying parities feels like bookkeeping, and I want to know which physical fact makes it a topological statement rather than a coincidence about symmetry labels.
The parities change only when a band at one of those momenta swaps with one of the opposite parity. 2 bands crossing and exchanging places. That is a band inversion, and it can only happen by the gap closing there. So the sign is constant under every deformation that keeps the insulator an insulator, which is the same protection clause as the Chern numbers. Different invariant, same escape route. You cannot walk it from one value to the other, you can only break the thing that defined it.
That gives me the bulk number back. It does not give me the thing I actually asked for. Does the twist force the edge, the way the Chern number forced its channel?
It does, and the argument is the one you already ran. The vacuum outside the crystal is even. The sign inside is odd. It cannot change while the gap stays open, so the gap has to close somewhere on the way out.
And a closed gap on a boundary where time reversal still holds is not a free choice. Whatever sits there has to come in Kramer's pairs. And one pair is exactly what an odd count means. Odd inside, even outside, one pair between them, and I did not have to look at the edge to know it was there.
That is the correspondence, and it is why the parity count is worth the trouble. Nobody has to grow the crystal. You compute 8 signs from a band structure, and you know whether the surface conducts.
The ingredient list has one item on it, and I have not yet been told how big it is. Spin-orbit coupling has to be strong enough to invert bands, and my memory of it from atomic physics is that it is a fine structure correction, a small splitting of spectral lines, the sort of thing you treat as a perturbation and then forget.
In hydrogen, yes, and that is exactly the wrong atom to have learned it on. The coupling grows ferociously with nuclear charge, roughly as the 4th power of atomic number, because the field near a heavy nucleus is enormous and the inner electrons move at a serious fraction of the speed of light. Carbon has 6 protons. Bismuth has 83. Take the ratio, raise it to the 4th power, and you are somewhere around 40,000.
So the effect is a footnote in the top of the periodic table and a structural feature at the bottom of it.
A structural feature, and it is why the entire subject is written in mercury, tellurium, bismuth, antimony, selenium, lead. It is also why Kane and Mellé's own proposal did not work. They chose graphene because the honeycomb was Haldane's lattice and the mathematics is clean there. Then people computed graphene's intrinsic spin-orbit gap. The first estimates came out around a millionth of an electron volt. The most careful later measurement puts it at a few tens of millionths. In temperature, between 1/100th of a Kelvin and about half a Kelvin.
Which is not a material, it is a footnote with a laboratory attached. So the theory arrived complete and pointing at a substance that could never show it.
Complete, correct, and unobservable, which is a particular kind of frustrating. The picture was right, the lattice was wrong, and the fix was to stop looking at the lightest element anybody had made a sheet of and start on the heaviest ones anybody could grow.
What are you actually looking for in a heavy material? Strong spin-orbit coupling is a property of an atom, and the invariant is a property of a band structure, and I do not see how one becomes the other.
You are looking for an inversion. In an ordinary semiconductor, the conduction band is built from the metal atom's s orbitals, round, symmetric, even under flipping coordinates, and the valence band from p orbitals, which are odd. Now let the spin-orbit coupling be strong enough to drag the p-derived states above the s-derived ones. The material is still an insulator, still gapped, but the 2 bands have swapped character. Even sits where odd used to. That is exactly the sign change the parity formula counts.
And you cannot get there from an ordinary insulator without the gap closing on the way, because the bands have to pass through each other to swap.
Which turns the whole thing into an engineering problem. Find a knob that drives the gap through 0, and the invariant has to change at the crossing. Bernavig, Hughes and Zhang, 2006. Their knob is a thickness. Mercury telluride and cadmium telluride are both semiconductors, growable in alternating layers to atomic precision. Bulk mercury telluride is already inverted. Its spin-orbit coupling is so violent that its bands sit in the wrong order relative to any normal semiconductor. Cadmium telluride is not.
So a thin layer of mercury telluride squeezed between cadmium telluride is dominated by its surroundings and behaves normally, and a thick layer is dominated by itself and stays inverted, and somewhere in between there is a thickness where the gap closes.
6.3 nanometers. About 20 atomic layers. Below it, an ordinary insulator with an even invariant and nothing on its edges. Above it, an odd invariant and a pair of helical channels running round the rim. And nobody has to search chemical space. You grow the same two materials in the same machine and change one number in the recipe, and the topology flips. A transition between two phases, where the control parameter is how long you leave the shutter open, is about as clean a proposal as this field has produced.
How long between the proposal and the measurement?
Under a year. Monenkamp's group at Würzburg had been growing mercury telluride wells for other reasons and had the best material in the world sitting in the building. Koenig and colleagues, 2007.
What does the experiment look like? Because a two-terminal conductance is a very blunt instrument for detecting a statement about parities in a band structure.
Blunt and completely decisive, which is the pleasure of it. You make a Hall bar out of the quantum well, put a gate on top to push the Fermi level into the bulk gap, cool it to a few hundredths of a Kelvin, and measure the conductance end to end. With the well thinner than critical, the conductance in the gap falls towards zero as you cool, which is what an insulator does. With the well thicker, it does not fall. It sits at a plateau near 2 times the electron charge squared over Planck's constant.
2, because there are 2 channels on the edge, one going each way, and each perfect channel carries 1 quantum of conductance, in resistance that is about 12,900 ohms.
Half of the von Klitzing constant in a device with no magnet attached to it. And 2 further checks in the same paper matter more than the number. First, the residual conductance does not depend on the width of the sample. Make the bar twice as wide and it is unchanged, which is impossible for anything carried through the bulk and inevitable for something carried on the rim. Second, apply a small magnetic field, a fraction of a Tesla, nothing by the standards of the previous subject, and the plateau is destroyed.
Destroyed by a field so small that it cannot possibly be doing anything to the band structure.
It is not touching the band structure. It is removing the symmetry. The protection is a consequence of time reversal, and a magnetic field breaks time reversal, so the Kramer's degeneracy at the crossing is no longer enforced. A gap opens on the edge, and the channel stops conducting. That sensitivity is not a weakness of the sample. It is the sharpest evidence that the mechanism is the one claimed, because an ordinary conducting edge would not care.
What else was done to nail it down? 2 terminals and a plateau feels like a lot of weight on one measurement.
Roth and the same group, 2 years later, did the measurement that convinces people who do not want to be convinced. Put 6 contacts on the bar. Drive a current between 2 of them and measure the voltage between 2 others nowhere near the current path. In any bulk conductor, that voltage is essentially nothing, because the current does not go there. On an edge channel, the current must run all the way round the perimeter, past every contact, so the far pair reads a large voltage, and the values match the arithmetic of channels running round a loop, each contact equilibrating them.
Now the honest question. The quantum Hall plateau was flat to parts in 10,000 million. Is this one?
It is not, and the shortfall is real and worth being precise about. The 2 quantum value comes out cleanly in short devices, a micron or so of edge. Push the length to tens of microns, and the conductance falls below the quantized value, sometimes badly, and it fluctuates. So the edge is not the perfect wire the argument promises. Something is scattering, over long distances, where elastic backscattering is supposed to be forbidden.
What is doing it?
The leading account is charge puddles. The bulk gap in these wells is small, a few tens of millielectron volts, and the disorder potential is comparable, so the gap closes locally here and there, and you get islands of charge just inside the edge. An electron can hop onto a puddle, sit there, come off with its spin scrambled, and continue the other way. Nothing in the symmetry argument forbids it. That argument is about a single electron bouncing elastically off a static potential, and a puddle holding a spin for a while is neither. There has been steady progress. Training the gate dielectric has pushed the scattering length past 100 microns, and the mechanism is still argued about.
So the protection is real, and the plateau is not a metrological standard. That is a fair distance from the way this material gets described.
A fair distance, and the distinction is what this hour is for. What is protected is that the edge modes exist and cannot be removed. What is not protected is that every electron sails along them without incident. The quantum Hall edge got both because its protection came from geometry. The backward channel was a millimeter away across an insulating bulk, and nothing local could reach it. Here it is a nanometer away, sitting on top of the forward one, and the only thing keeping them apart is a symmetry.
A nanometer away, and it still cannot turn round. That is the claim I want taken apart slowly, because on the face of it, it is absurd. Two states at the same energy on the same edge, overlapping in space, and an impurity that connects everything to everything. What exactly is the number that comes out zero?
Set the impurity down and ask what it can do. It is a lump of potential, a missing atom, a stray charge, a bit of roughness. It pushes on the electron's charge. It has no magnetism, so it does not push on the spin at all. As an operator, it is the identity in spin space. The electron arriving is a right mover with its spin up, because the material has locked those two together. To reverse it, you must put it into the only other state available at that energy, the left mover, and the left mover's spin points down.
And the potential cannot flip the spin, so the overlap between the state you have and the state you need is zero, because up and down are orthogonal.
That is the argument in short form, and it is correct. But it makes the zero look like an accident of the spins happening to be anti-parallel, and it is not. The left mover is the time reverse of the right mover. That is what a Kramer's pair means. And there is a general statement about time reversal invariant operators sandwiched between the two members of a Kramer's pair when the particles have half-integer spin. The matrix element is exactly zero, not suppressed by a small parameter. Zero by the same algebra that gives you Kramer's theorem.
I would like the mechanism rather than the algebra. When two amplitudes cancel, there is usually a picture of two paths and a relative phase.
There is, and it is the best picture in the subject. The electron meets the impurity and can go round it either way, clockwise or anti-clockwise. Both routes end in the same place, moving backwards, so both contribute to the reflected amplitude. Along the way, its spin is dragged round with its momentum because they are locked, so the clockwise route rotates the spin half a turn one way and the anti-clockwise route half a turn the other. The two arriving amplitudes differ by a full turn of the spin.
And a spin half object rotated through a full turn comes back as minus itself.
Comes back as minus itself. So the two ways round the impurity arrive exactly out of phase and cancel exactly. That is why the zero is exact rather than approximate. It is destructive interference enforced by the fact that a full rotation is not the identity for a spin one half. Every attempt to reflect is two attempts, and they annihilate.
The full turn minus sign is normally shown to me as a curiosity, the neutron interferometer, the coffee cup trick. This is the first time I have seen it hold something up.
It is holding a conductor up, and the same picture tells you what breaks it, which matters more than the protection itself. Put a magnetic impurity on the edge instead, an iron atom, a spin of its own. It is no longer a scalar in spin space. It can flip the electron's spin as it passes, and the argument evaporates in one line. Reversing the momentum no longer requires anything forbidden, and the electron turns round.
One atom, and it is finished?
One atom scatters one electron. Real damage needs enough of them, or a field, or magnetic order in the material. But the point stands in its sharpest form. The entire protection rests on a symmetry. Anything magnetic removes that symmetry, and there is nothing underneath it. The state does not degrade gracefully. It stops being the state.
Compare the two cases because I think I have been treating them as the same object, and they are not. The Chern number in a magnetic field, and this.
They differ in the way that matters most. The Chern number needs no symmetry whatsoever. Add any perturbation you like: impurities, interactions, strain, a bent edge, a badly soldered contact, and as long as the bulk gap survives, the integer is exactly what it was. Nothing is forbidden. There is simply nothing that can change the answer.
And this one comes with a condition attached to it. So the honest statement is not protected, but protected as long as.
As long as time reversal holds, which is a condition on the environment and not only on the sample. That is what symmetry protected means, and it is a genuine category rather than a hedge. There is a whole classification of such phases, protected by time reversal, by particle hole symmetry, by a crystal symmetry like a mirror plane, each with its own list of what you must not do.
What must I not do here exactly? I want the list because do not break time reversal is not something I can check on a bench.
Apply a magnetic field of any size in any direction. Dope it with magnetic atoms or let a magnetic layer touch it. Cool it into a magnetically ordered state of its own. Those are the three ways in, and all of them are things a laboratory does routinely without thinking of them as symmetry operations. Not on the list. Heating it, bending it, making it filthy with ordinary impurities, changing its shape. None of those touch the invariant.
There is something almost perverse in the fact that the thing which destroys this state is exactly the thing which created the state we started the hour with.
Not a coincidence, and the cleanest demonstration that the symmetry argument is right rather than merely consistent. Put magnetic atoms into a topological insulator and you break time reversal deliberately. Photoemission shows the surface crossing opening into a gap. Chern and colleagues did that with manganese in bismuth selenide in 2010, a few milli-electron volts where the crossing had been. Do it in a thin film and cool far enough, and you land in Haldane's phase, a Chern insulator with a chiral edge and a quantized Hall resistance at zero field. Chang's experiment, the one that finally built the model this hour opened with, is a topological insulator with its protecting symmetry destroyed on purpose.
The two phases are neighbours, and the road between them runs through breaking the symmetry.
One more distinction, and the picture is complete. Neither of these is what the fractional states have. A Chern insulator and a Z2 insulator are both, underneath, independent electrons filling bands. The topology is a label on a band structure, computable without ever writing down an interaction. The fractional states have topological order in the deeper sense, a ground state degenerate in a way that depends on the shape of the space, excitations carrying a fraction of the charge, and no band structure anywhere in the account. A different kind of object, and it needs interactions to exist at all.
Symmetry-protected topology is a property a band insulator can have. Topological order is a property only a genuinely many-body state can have.
Which is the sentence to keep, and it costs the symmetry-protected phases nothing to admit it. They are far easier to find, they exist at room temperature in real crystals, and they are the reason this became a material subject rather than a corner of mathematical physics.
Everything so far has been two-dimensional, a sheet with a one-dimensional rim, which is the geometry the whole Hall business was written in. But the material I was promised at the end of the last hour is a lump, an insulator with a metal skin sitting on a bench. It has faces, not edges, and I do not think the argument carries over for free because the counting I used was about channels along a line, and a face is not a line. What happens when the insulator is three-dimensional?
3 independent groups got there within about a year of each other. Fu, Kane and Melee, Moore and Balance, and Rahul Roy in parallel. In 3 dimensions, there are 4 invariants rather than 1, which makes 16 classes rather than 2. 3 of them are what you get by stacking planes of two-dimensional systems, and those are called weak because disorder can undo the stacking. The 4th is called strong, and it is the one with no two-dimensional parent.
What does a strong one look like from the outside? For the two-dimensional case, I could count channels round the rim, and I could say which way each was going and what spin it carried. On a face, I have a two-dimensional surface with a continuum of directions available and no obvious thing to count.
What lives on the face of a strong topological insulator is a metal with a particular band structure. The energy rises linearly with momentum away from a single point, in every direction. A cone rather than a parabola. Electrons in it have no mass in the usual sense. The dispersion is a massless relativistic particles, so it is called a Dirac cone. And the spin is locked to the momentum here too, in the two-dimensional way. It lies in the plane of the surface at right angles to the direction of travel and wins once round as you go once round the cone.
Once round. So an electron on the far side of the cone, moving the opposite way, has its spin pointing the opposite way, which is the same locking as before, dressed for a bigger stage. The exact reversal is forbidden, and everything short of it is only partly allowed. And the winding is presumably the thing that is odd rather than even.
The odd thing is the number of cones. A surface can host 1, or 3, or 5, and none of those can be removed. 2 can be removed, or 4, by the same argument that gapped out your 2 pairs of edge channels. Cones can be pushed together and annihilated in couples. So the invariant is whether the number of cones is odd, and the strong topological insulator is the case where it is.
A single Dirac cone. There is something wrong with that, or at least something I was taught was impossible. If I try to write down a lattice model in 2 dimensions with time reversal symmetry and put one Dirac cone in it, I cannot. They come in pairs. Graphene has 2 at opposite corners of the zone. That is a theorem, not an accident of the models people happen to write.
It is a theorem called fermion doubling, and it is why the single cone is the most striking claim in the subject. You cannot build a lone Dirac cone out of a 2-dimensional crystal. You can put one on the boundary of a 3-dimensional one, and then the partner is not absent. It is on the opposite face, centimeters away. The surface does something no freestanding 2-dimensional material is permitted to do, and it gets away with it because it is not freestanding.
Which also tells me what would happen if I tried to gap that cone. To open a gap at the crossing point, I would need a term that behaves like a mass, and a mass term for a Dirac cone has to break time reversal, or there is nothing for it to be.
There is nothing for it to be. Every mass you can write for a single Dirac cone is odd under time reversal. That is the whole protection restated on the surface. An ordinary perturbation cannot gap it, a magnetic one can, and the gap it opens is the one photoemission sees when you put manganese on the surface.
How was any of this actually observed? A statement about parities at 8 momenta is a long way from a measurement, and a conductance plateau in a quantum well was 2-dimensional. For a 3-dimensional crystal with a conducting skin, I need a probe that looks only at the skin and reports back what the electrons there are doing.
Photoemission, which this course has already used for quasi-particles. Shine ultraviolet light on the crystal, knock electrons out, and measure the energy and angle of each one that comes off. Those give you energy and momentum, so what you collect, event by event, is the band structure itself. And it is naturally a surface probe, because an electron excited deep in the crystal does not escape. The escape depth is a nanometer or so.
So the states we care about are the only ones it sees clearly, which is unusually convenient. What did it show?
The first one is the untidy one. David Shea, Zahid Hassan and colleagues, 2008, on an alloy of bismuth and antimony. They counted 5 surface bands crossing the Fermi level between 2 of the special momenta. 5 is not a beautiful number, and the surface structure is genuinely complicated, and that is exactly why it counted. 5 is odd, and odd is the claim. An ordinary material's surface bands cross an even number of times.
An ugly measurement of a clean statement. Though 5 bands is a lot of apparatus to hang a parity argument on, and I imagine everybody wanted the simple case.
Everybody wanted the simple case, and it arrived within the year. Shia, Hassan and colleagues, 2009, on bismuth selenide, a compound anybody can grow, 2 elements layered so it cleaves like mica, and you get a fresh, clean surface by pulling sticky tape off it. 1 Dirac cone at the center of the surface zone, and a bulk gap of about 0.3 of an electron volt, more than 10 times the thermal energy at room temperature.
More than 10 times. So the topology is not a low-temperature phenomenon in that material at all. The gap is not the thing that needs a cryostat. Whatever else is difficult about working with it, keeping the phase alive is not.
A theory paper from Haijun Zhang, Shu-Cheng Zhang, and collaborators arrived alongside it, predicting the same for bismuth selenide, bismuth telluride, and antimony telluride. Between them, the subject acquired a workhorse material within a year of acquiring the idea. Spin-resolved photoemission followed, the harder version of the same experiment. You measure not just the electron's energy and momentum, but which way its spin was pointing. The spin wins once round the cone, exactly as the picture demanded.
That is the band structure confirmed. It is not the transport statement, though, and the transport statement is the one with the physics in it, that an electron on this surface cannot be turned round. Photoemission removes electrons from the crystal. It cannot watch one bounce off an impurity.
Which is where the other probe comes in. A scanning tunneling microscope is a needle sharpened to a single atom, held a fraction of a nanometer above a surface, with a voltage between the two. Electrons tunnel across the gap, and the current depends exponentially on the distance. Change the height by 1 atomic diameter, and it changes by about a factor of 1,000. So you hold the current fixed with a feedback loop and let the tip trace out the surface, atom by atom. That is the imaging mode everybody has seen pictures from.
Exponential sensitivity is the whole instrument then, but an image of atoms is a picture of where the nuclei are, and I want to know what the electrons are doing.
Change the voltage instead of the height, and the current tells you how many states there are at that energy, at that point on the surface. Now put an impurity on an otherwise perfect surface and map the states around it. The incoming wave and the scattered wave produce a standing wave pattern, ripples spreading from the impurity, exactly like water round a post. Their wavelength tells you the difference between the incoming and outgoing momenta.
So the ripple pattern is a record of which scattering events actually happen. Take the pattern apart into its component wavelengths, and each one corresponds to one pair of states on the cone that the impurity managed to connect.
And Rushan, Yazdani, and colleagues did that in 2009 and found one component missing. The ripples that would correspond to scattering from one side of the cone to the exactly opposite side, the backscattering wavelength, the shortest available, are absent. Every other angle is represented and gets weaker the closer it comes to a reversal. It is the forbidden transition, photographed as a whole in a Fourier transform.
An absence you can point at. That is a much better piece of evidence than a plateau, because a plateau is a number that could have several parents, and this is the specific process being visibly ruled out.
Now the part that has to be said about all of it. Bismuth selenide, the material that made the subject practical, is not an insulator. It grows with selenium vacancies, each donating electrons, so the Fermi level sits up inside the conduction band and the bulk conducts perfectly well. In a transport measurement, the surface is a minority share of a current running mostly through the interior. Photoemission does not care because it only ever sees the surface. Transport cares enormously.
So the name is a claim about the band structure, not a description of the sample, which is a strange position to be in. The material was chosen because it was the clean case, and the clean case has a bulk that shorts out the effect you are trying to measure.
That is a fair summary of a decade of hard materials work. Compensation doping, alloying bismuth against antimony, thinner films, better growth, all aimed at pushing the Fermi level back into the gap. It has improved a great deal, and it is not solved. When you read a claim about surface transport in one of these, the first question is always how much of the current went through the middle.
There is one more thing this hour owes, and it is the reason a lot of people outside the field have heard of any of this at all. Somewhere in here there is supposed to be a particle that is its own antiparticle, and a quantum computer that cannot forget. What is the physics before the promises?
The physics starts in 2001 with Alexei Kitaev, and it is a toy model in the honorable sense. A chain of sites with electrons hopping along it, and a superconducting pairing term of a particular kind. Every electron operator splits into two halves that are each their own conjugate. An operator equal to its own adjoint, which is the algebraic content of its own antiparticle. Ordinarily, that is bookkeeping. The halves sit on the same site and recombine into the electron you started with.
And in Kitaev's chain, they do not recombine on the same site.
At the special point of his model, each half pairs with a half on the neighboring site. Run that down the chain, and every half is spoken for except two, one at each end. Those two cost no energy, and together they make one ordinary fermionic state delocalized over the two ends of the wire with nothing in between.
One state split into two pieces at opposite ends of an object. So the system has two ground states, the state with that fermion present and the state with it absent, exactly degenerate, and the difference between them is not sitting anywhere in particular. If I want to know which one I am in, looking at one end of the wire cannot tell me, because the information is a joint property of both ends.
That is the whole idea, and you have it. The degeneracy is not exact for a finite wire. The two ends can feel each other, and the splitting falls off exponentially with the length in units of the superconducting coherence length. Exponentially exact rather than perfectly exact, which for a wire a few microns long is a very good deal.
Why does that make a robust qubit? I can see that it is hard to read, and hard to read is not obviously the same as hard to disturb.
It is the same thing, and that is the point. Decoherence is the environment reading your qubit without permission. A stray charge, a phonon, a fluctuating field, each acts locally, and a local operator at one end of the wire cannot distinguish the two ground states because the distinction is not located there. To flip this qubit, the environment would have to act on both ends coherently at once. Noise does not do that.
So the protection is the same trick as the edge channel, moved into a different problem. There, the backward state existed but was unreachable. Here, the information exists but is unreadable. And in both cases, the safety comes from the thing you would need to touch being somewhere else. And I take it the operations on it are supposed to inherit the same character.
Exchange two of these modes, and the state does not merely pick up a phase. It is rotated within the degenerate space, and which rotation depends only on which mode went round which. Not on how fast, not on the exact path, not on the details of the pulse. A gate specified by topology rather than by timing. That is what a topological qubit means, and it is why serious money has gone into it for 20 years. Braiding alone does not give you every gate you need. A supplementary operation is required, and that one is not protected.
How do you build it, given that Kitaev's chain has a kind of superconductivity that does not occur in nature?
Two routes, both out of this hour's material. Fu and Kane, 2008, put an ordinary superconductor against a topological insulator's surface and the spin-momentum-locked surface state converts the ordinary pairing into the exotic kind, and a vortex in it traps one of these modes. The second route, 2010, replaces the topological insulator with an ordinary semiconductor nanowire with strong spin-orbit coupling, plus a superconductor on top and a magnetic field along it. That is the one everybody built, because indium arsenide and indium antimonide nanowires with aluminium shells are things a growth laboratory can make.
And where does the experimental claim stand? I want the position stated plainly rather than either sold to me or sneered at.
Claim me then. In 2012, Morik and Cohenhoven's group at Delft reported a conductance peak at exactly 0 voltage in such a wire, appearing when the field was turned on and staying pinned as field and gate were varied. That is the theory's prediction, and it started the boom. It is also something ordinary non-topological states in a disordered wire can reproduce. An accidental quantum dot near the contact gives a zero-energy state that looks the same. In 2018, the same group reported the stronger signature, the peak quantized at the predicted value, and it was retracted in 2021 after outside physicists got the raw data and found figures selected and adjusted and contradicting data left out. A separate high-profile claim on a different platform was retracted in 2022. In 2025, a large industrial group published a parity measurement, with an unusual note from the journal saying it did not establish that Ra-Ner modes were present. A published comment argues the test used to declare those devices topological gives different verdicts on the same data for choices that should not matter, and that the readout itself was done in a region the transport says is gapless. The group replied in the same issue. That argument is live.
What has not been done, so I know what the missing measurement is?
Braiding. Nobody has exchanged two of these modes and demonstrated the resulting rotation, which is the operation the entire proposal is about, and which no trivial state can imitate. So the position is this: the theory is solid and not in doubt, a consequence of pairing and symmetry that people have checked from several directions. Whether any device built so far has ever contained one of these modes is not established. Both halves of that sentence are load-bearing.
The gap between a beautiful theory and a confirmed object, then. And it is a different situation from everything else in the hour, because the quantum spin Hall plateau and the single Dirac cone were measured, argued over, and are now simply facts about materials.
Which is the right comparison to end on. The insulator with the conducting skin is settled physics, with textbooks and standard materials and thousands of samples. The topological qubit is a proposal with 2 decades of effort behind it and no confirmed instance. They live in the same subject, and they are not in the same condition.
3 things I would want to be held to. What symmetry protection buys you is existence. The edge modes cannot be removed, no matter what non-magnetic mess you make of the sample, because removing them would mean removing an odd number of Kramer's pairs, 2 at a time, and the arithmetic does not permit it. What breaks it is anything magnetic, a field of any size, magnetic dopants, magnetic order. And when it breaks, there is nothing left underneath, unlike the Chern number, which needs no symmetry and therefore has nothing to lose.
And the second.
The helical edge resists disorder because turning an electron round means reversing its spin as well as its momentum, and an ordinary impurity has no way to touch a spin. Put more carefully, the 2 ways round the impurity rotate the spin a full turn relative to each other. A spin 1/2 rotated through a full turn changes sign, and the 2 reflected amplitudes cancel exactly. And the third, a Ra-Ner mode, makes a robust qubit, because the bit is stored jointly in 2 objects far apart, so nothing acting in one place can either read it or disturb it, and the operations on it depend on the topology of how you move things, rather than on how carefully you move them.
That is the hour, and there is one loose thread in it that is going to become the next subject. Every protected object we have discussed carried a conductance, and every one of them carried the same unit, the electron charge squared over Planck's constant. 1 quantum per chiral channel in a magnet, 2 quanta for the helical pair at zero field. That unit has been arriving all hour, and it has never once been derived from anything topological.
It has not. It came out of the constants by dimensional analysis in the Hall bar, and it has been reappearing ever since. And I have been treating it as a property of these exotic states, where nothing in the argument says it belongs to them.
It does not belong to them. So take a wire, not a topological anything, a wire. A meter of copper, and the first rule anybody learns about conduction. Halve the length and you halve the resistance. Halve it again and again. There is a length at which that stops being true, and the reason has nothing to do with symmetry, or invariance, or spin. A perfect edge channel has a resistance that does not depend on its length at all, which is already a flat contradiction of that rule, and the contradiction was never topological. It was there in the word channel.
So the thing to go and look at is an ordinary conductor shrunk until the number of electrons crossing it is a number I could say out loud, where the current has to arrive through a countable set of ways through, and Ohm's law fails for reasons that were sitting inside it the whole time.